So we've learned the definition of z-score. Namely, it's one of these two formulas. And what's more important is that it gives you a good sense of your position in a data set. It can tell you whether you're equal to the mean, below the mean, or above the mean, but it also gives you a sense of how far away from the mean you are. So is your value far above the mean? So having a z-score of 2, 2.5, 2.75, 3, 3.5, etc. Or far below the mean, -3, -2.5, and so on. So it gives you a sense of where you fall in the order of the data set. So now let's expand upon that idea for an example. So the mean height of males 20 years or older in the US is 69.2 inches with a standard deviation of 2.9 inches. The mean height of females 20 years or older in the US is 64 inches with a standard deviation of 2.75 inches. Now Edward is 6 foot 1 inch and Bella is 5 foot 8 inches tall. Who is absolutely taller? All right, absolute means you're going to compare them directly to each other. So when you make a direct comparison, so let me make that absolute means direct comparison. Well, obviously he's taller. He's 6 foot 1, she's only 5 foot 8. So if you put them next to each other, he will be taller. He'll be taller by several inches, by 5 inches to be precise. So Edward is taller. That said, it's not really fair to compare the two of them. Men are taller on average, so it's not really surprising that he's taller, right? We expect him to be taller. All right, so comparing raw heights is not really fair because they're actually part of different groups. So, in other words, they each belong as part of their own separate group, and each of those groups has its own average where the men are taller. So it's not really fair to directly compare them. As a matter of fact, you can think of a whole bunch of variables, and we can just stick with the male-female thing for a second. There's a whole bunch of things that's not really fair to directly compare them, perhaps. Some of these might be arguable. So, for example, the age when you first get married, the age when your first child was born. There might be biological reasons for why it would be younger in one group than another. Weight, shoe size, endurance, pain level, etc., etc., etc. There's just a variety of things that were just different groups. And so perhaps for various reasons it might not be fair to compare them. As a matter of fact, there's a lot of things that it would not be fair to compare. So the classic, of course, is apples and oranges, right? So that's literally what I'm getting at. So apples and oranges, not fair, right? They're different fruit. They belong in each of their own categories. Anybody in the US, you might have taken the SAT or the ACT. Those are both tests you take when you graduate from high school or close to graduation time. And they're completely out of different scores. The ACT is out of something like 36, and the SAT is out of like 1600. You can't really compare them. And then, of course, my favorite from my Halloween days when I was a kid, the plain versus the peanut. I mean, everybody knows when you open, a bag of fun-sized peanut M&Ms, there's just not much in there, right? Not in terms of number of M&Ms, right? All right, so now that leads to the question saying, okay, if it's not really fair to directly compare them, then let's look at who's relatively taller. So when we see relative, that means that we're going to use z-scores. Z-scores, sorry about that. Okay, so we'll use z-scores. We can do that. So let's find the z-score for each one of them. Well, the first thing you're going to have to do is convert them because the height averages, let's put it up here real quick. So we note that for men and for women, the men height average is 69.2. Now it kind of implies that this is for all men in the US. So that would be a mu and a sigma that you're given, and same for the females. So let me type that up 1 second. All right, so the men's average is 69.2, the women's average is 64, the men's standard deviation is 2.9, and the women's standard deviation is 2.75. And I figured out from context, I realize that this is a population, right? Not a sample. Okay, all right. And then I also realized, hey, these are not given to me in feet and inches. So I'm going to have to convert both Edward's and Bella's height to just straight inches. So he's 6'1". There's 12 inches in a foot. So it's 6 times 12 plus 1, which is 73 inches tall for him. She is 5 feet 8 inches tall. So she's 5 times 12 plus 8, which is 68 inches tall. All right, so now for the z-score formula, I'm going to use whichever one's appropriate for my situation. Since I'm dealing with a population, this is the one I'm going to use, right? But if it was sample data, it wouldn't have really changed the problem. I just used that one instead. But we're using a population value here. It's implied, right, that this was a population. All right, so Edward would be x minus mu divided by sigma. Now, the number one mistake students make on this problem is they don't type this correctly in a calculator. So let me bring up a calculator. Okay, so there's two ways to do this correctly. So you can use the parentheses. 73 minus 69.2, close your parentheses, divided by 2.9. I cannot stress this enough. Use the parentheses. The parentheses, this numerator here is grouped together as far as mathematics is concerned. That is a parentheses. This big old division bar right there, that's a parentheses. It's a grouping symbol. So use parentheses when you do that calculation. Or you can use, if you have a TID4, alpha F1, pick number 1, numerator over denominator, take 73 minus 69.2, use your downward arrow, type 2.9, enter, and there you have it. Now Bella is going to be 68, so I'm going to hit alpha. I'm not going to hit alpha. Let me quit and get out of there. There we go. Alpha F1, number 1. She's 68 minus, now for women it was 64 as their average, divided by 2.75. And you can see that she's 1.4545, repeating. So that's her z-score. And as it said on the previous page, we generally round z-scores to 2 to 3 decimal places. 2 did just fine here. So now who's relatively taller? Well, Bella is, right? She's actually relatively taller. She's taller in relation to her group than he is in relation to his. And the z-score showed that. She had a larger z-score than his. Right? In other words, if you compare her to other women and him to other men, she's the taller one. Now, just in case you're wondering, Edward and Bella is a Twilight reference, and Kristen Stewart is actually nowhere near 5 feet 8 inches tall. I faked this data to get this to work right. So Kristen Stewart's much smaller than that. But for our purposes, this works great. I choose to believe this is the Edward and the Bella from the books. There you go. All right, so now let's go look at 2 Olympic gymnasts. Now, if you know anything about gymnastics, you know that for various reasons, it's very wise to have them be quite short. It has to do with the center of gravity and physics when they're tumbling and so on. Now, Simone Biles, often considered one of the greatest gymnasts of all time, she is only 4 feet 9 inches tall. One of our greatest male gymnasts of all time in the U.S. is a male gymnast named Daniel Leva, and he is 5 feet 7 inches tall, and his last name got lost off of this, but it's Leva. I can tell you what it is. And he won Olympic bronze overall, and I think he's actually won some silvers in some particular events. Anyway, who is relatively taller? I mean, obviously he's taller, period, right? I mean, he's just straight up several inches taller than her, right? But the question is, who is relatively taller? And are either one of them unusually short? Now, we expect both of them to be short because they're gymnasts, but are they unusually short? So let's start by finding their z-scores. The first thing we do is, just like with the other two, we convert them to inches. So 5 times 12 plus 7 is 67 inches, and 4 times 12 plus 9 is 57 inches. So he's actually 10 inches taller than her. But they're both short people. They're both below average. Now, Daniel would be 67 minus 69.2. So let me type that in. Alpha F1. Pick number 1. 67 minus 69.2 divided by the average for men, so 2.9, and he's at negative 0.7586. We're not shocked. It's negative because he's short. relatively speaking. He's a gymnast. Now her value is going to be, I'll use the parentheses for her just to give us some variety. So parentheses 57 minus 64, close parentheses, divide by 2.75. And there she is. All right, so who's relatively taller? He is. I mean, they're both short, but he's relatively taller because he's less negative than her. Right? In other words, his z-score is to the right of hers on a number line. Right? Keep in mind they're both short because they're both negative, or they both have negative z-scores. Actually, I just wrote that right from the beginning. So they're both short because they both have negative z-scores, but Daniel is relatively taller. His z-score is less negative than hers. He's close to the mean, and she's actually far away from the mean, right? And if you look at his numbers, it makes sense. He's at 67 inches. He's only a couple inches shorter than the average for a man, whereas she is 4 feet 9 inches tall. She is very tiny compared to the average height for a woman, which is 64 inches tall. And as for unusual, well, let's remind ourselves about what unusual looks like. Unusual would be being more than 2 standard deviations away. So if you have very large unusual values, that would mean that your z-score is greater than 2, right? Because that's more than 2 standard deviations above. If we remember that from back in section 3.2. Now, very small values would be z is less than negative 2, right? Because that's more than 2 standard deviations below. So if we look here, who's unusual? Simone is unusual. So Daniel is relatively taller, right there, but Simone is unusually short. Oh, let me type that up 1 second. There we go. Her z-score is below negative 2, right? So another way to put that is that the magnitude, the absolute value, magnitude of a z-score is the distance the z-score is from the mean. And another way to see it is that the absolute value of her z-score, if you take the absolute value of negative 2.5, you get positive 2.5, and that is greater than 2. So let me just draw you a picture real quick. It's coming in. There you have it. So z greater than 2 over here, z less than negative 2 over here. The absolute value is greater than 2 for both sides, right? Because you're farther than 2 away from the mean. The mean is at the center. The z-score is 0 at the center. And then if you're farther than 2 away from that, then you're unusual. And there we have it. So now let's look at Yao Ming. He is a former center. I do not believe he is currently playing. So he's a former center for the from China, from the Houston Rockets. The Houston Rockets being a basketball team. He was 7 feet 6 inches tall. What is his z-score? Well, let's start off with making a conversion. 7 feet times 12 inches plus 6 makes 90 inches tall. So he's 90 inches tall. So if I take 90 and I subtract 69.2 and I divide it by 2.9. Oops, divide. There we go. 7.17. Did you catch that? Right? We just said above that anything past 2 standard deviations is unusual. He's very, very unusual. He's extremely unusually tall. He was so unusually tall, in fact, that when he would step onto the court originally, people would just kind of like, it's startling, right? He's so tall that it's the startling kind of tall. If you've ever been at a restaurant or something like that and somebody walked by who was just really, really tall, it's just, you just kind of notice it, right? Because it's just so startling to see. All right, so he's far, far past 2 standard deviations. I mean, 2 standard deviations is our threshold for unusual, and he's there. Now, that said, he was in a sport, a profession that prizes height. So what if we don't compare him to all people? That doesn't seem fair. What if we compare him to other NBA players, to his peers? Well, NBA players have an average of 6'7" inches tall and a standard deviation of 3.5. So again, from context, we can assume that those are population values. Sorry, I just copied and pasted the old one. So those are population values. So now what is his z-score in comparison to the group? Well, we do what we just did, but instead of his height hasn't changed, it's still 90. But instead of 69.2, we use 79. I got that, by the way, by 6 times 12 plus 7. Here, let me show you real quick. So that's where that came from, right? So that's where the 79 comes from. And then I subtract 79, I divide it by 3.5. They've got a little bit more standard deviation. It's a smaller group. And there you have it. He's 3.1428. That is his z-score. So he's still unusually tall, even when you compare him to just NBA players. But it's not as dramatic as it is when you compare him to the population at large. There we go.